a process for charging a battery, and this process is a dissipative process. So let me say that a battery, I will consider a battery a system that we use to store energy, and this energy, the amount of, so how charged is the battery is measured by the ergotropy of the battery, which was a quantity discussed by Mauro Paternostro this morning. So I will repeat a little bit what he said. The idea is that we have a battery which is has a Hamiltonian. It is in a system, in a state, and if applying a cyclic unitary transformation, we can reduce the energy of the battery. It means that the agent that applied this unitary extracted the work, right? So he can use it. And the idea of having a cyclic unitary operation is that the variables that control the agent return to their initial value, so he can compare the amount of energy he had before the operation and after the operation. And this means that the Hamiltonian of the battery remains the same. And the ergotropy is the maximal amount of work that you can extract, so you optimize over this possible unitary process. And we say that the system is a battery if it has ergotropy. So then it means that ρS is active, and if there is no ergotropy, then the system is passive and work cannot be extracted by this cyclic unitary process. So batteries have been studied in this context, like how fast I can implement the unitary to extract the work, etc. And most of the focus has been on the properties of the state of the battery that help to have a fast process, discharging process, for instance, or a fast charging process. So then the people discuss, so these are few references, there are much more, the quantum properties of the system that help, like entanglement, coherence, etc. But what I want to do is something different, is to ask if we can consider the system as an open system and engineer a dissipative process such that the system by itself, or not by itself, sorry, the system reach a state which is active, right? So the advantage could be that any initial condition will arrive to this active state, etc. And the answer is, of course, yes, because we can imagine easily that these dissipators here reflect the contact of the system to two heat baths. So the rho infinity in this case is a non-equilibrium steady state, and non-equilibrium steady states are usually active. So to do the question a little bit less trivial, I restrict myself to systems that are in contact with a thermal bath, a single thermal bath, right? So then, can this state be active? And again, yes, because we can have a non-equilibrium steady state when the system is in contact with a thermal bath. But in that case, it's a little bit silly because to have a non-equilibrium steady state, we have to dissipate work to keep the system in the steady state, right? So this is a classification of stationary states when the system is in contact with a single heat bath. It can be a non-equilibrium steady state if we are forcing and this energy is dissipated to the bath, right? So such that the energy of the system doesn't change, the entropy of the system doesn't change because it's a steady state. But in this case, it's a non-equilibrium steady state. And it is an equilibrium state when these quantities vanish. The system is there, nobody do work over the system, the energy stay constant, doesn't go as heat to the bath. So the interesting case will be to have that this system will be active and to be an equilibrium state. So now it comes the less trivial question is if it is possible to have an active equilibrium state, a state of thermodynamic equilibrium. So the first things that come to the mind is that the Gibbs state is passive, right? So the Gibbs state cannot be a system in the Gibbs state. It's not a battery. And one can link also the second law of the thermodynamics to the passivity of the equilibrium state. And so because we are thinking in a single reservoir, I consider this statement for the second law, that one cannot extract heat from a system for a heat bath at a fixed temperature, a single temperature, and transform it into work. Or in a cycle, the work that we do has to be positive, right? So this is the second law. And the link with passivity is the following. We start, so this is a cycle. There are 1, 2, 3, 4, and 4 is the same situation that 1. So we did a cycle. And the steps are the following. The battery is in a state of thermodynamic equilibrium with the system at a fixed temperature T, a given temperature. Then we do this unitary process that we want to use to extract the energy. So the energy change of the battery will be delta E, and if we extract energy, this delta E will be negative. Then the battery is in this rho prime state. We put it in contact with the thermal bath again, and we let the system to relax until we reach the same equilibrium state that we have here at the beginning. And therefore, the second law, which says that the total work performed in this cycle has to be positive, means that this delta E has to be positive. Therefore, we cannot extract work, right? So this is the link between passivity and the second law. But the important thing here is that we are considering states that relax to equilibrium. So the statement I will say is that from the second law, we conclude that systems that relax to equilibrium are passive. So, and by relaxation, I mean that this arrow happens with the agent doing nothing on the system. The agent just put the battery in contact with the bath and leave this process to go on by itself. But if we can engineer a thermodynamic process such that this convergence to the state of thermodynamic equilibrium happens with the agent doing some work to reach there, then the second law does not restrict the value of delta E, and delta E could be negative, right? So the second law does not imply necessarily the passivity of the equilibrium state. But what I have to do now is to convince you that we can have processes where this is possible. So what I have to show is I can drive a system from this state to that state, and that this state is a true thermodynamic equilibrium. Once the system is there in this equilibrium state, it stays there. The agent doesn't need to do work to keep it in equilibrium. There is no entropy production, no heat flow to the bath, etc. It's a bona fide equilibrium state. So to do that, this will be more kind of technical part, but I will show you that this is possible. And so the thermodynamic process I will consider were already discussed here. So we have our system of interest, which interact with a thermal bath. So I will imagine that I have many copies of this HB in the thermal state, and they interact and they evolve according to this unitary transformation. This unitary transformation is implemented by an agent that controls the interaction energy between the system and the battery, and it has to connect it and disconnect it, right? So this is where the agent will do work. Because all the work is done by this energy coupling, we will find things that are not the standard things that one expects to have in the weak coupling. So that's a remark I want to make. And so then we have these two systems that evolve together. We trace the path, and we have a dynamics for the system. This is a map that we iterate. And what we want is to have a map that, if we iterate, converge to a fixed point, a stationary state. And we want this stationary state to be a state of thermodynamic equilibrium, right? So just to emphasize, these iterations is like that. We have the system with the bath, it evolves, we trace the bath, we have the system in the new state, and we plug this ρs at time tau here, and we repeat the coupling with a new copy of the bath. We do the unitary, we trace, and etc. This is how this iteration is done. Now, the thermodynamics of that fundamental step, so because we repeat this step, so I call it the fundamental step, was discussed here by Gabriel Landi, by Tony Short. It's the same that I'm used here, so the heat that goes from the bath to the system is the energy change of the bath. The work is the total, the changing of energy in the total system, so it is what you need to have the first law. The entropy is Shannon entropy, and the entropy splits in two terms. One is the entropy production, which has this form, which is positive, and the entropy flux is given by the heat flow. So this is the kind of standard thermodynamics for this process. And then I ask, well, if I have a steady state, stationary state, it will be a non-equilibrium steady state when I'm dissipating work, or equivalently, the entropy production is positive. So in this fundamental step, the entropy production will be positive if it is a non-equilibrium steady state. But if it is an equilibrium state, the entropy production in this, when I apply the map, should be 0, right? So this gives me a condition to have an equilibrium state, and one can show that this condition is equivalently to ask that the unitary commutes with a sum where you have a system operator and the Hamiltonian of the bath. And if you find a system operator, I call it H0, that fulfill this, you will have a system with an equilibrium state, and the equilibrium will be this expression here. So the simple example is our thermal maps, where this system operator is the system Hamiltonian, right? And then the equilibrium state is the Gibbs state. Okay, so this is what I need to ask. I'm engineering these dynamics that will bring me to this equilibrium state. So I need to have a U that with an H0. And when I have a U, when I have a U and an H0, I can show that the thermodynamic quantities that I mentioned you before, the heat, the work in each fundamental step, I can write them in a simpler form, because the previous form involved not only the system but also the bath. This expression only involves properties of the system, where you have here the work in the step that goes from n-1 tau to n tau in time. This is the heat, this is the entropy production, will be positive. So you see again that if H0 is the system Hamiltonian, there is no work. This will be kind of a relaxation process, and you recover the well-known expressions, right? Okay, so if I add all the contributions of, so I starting with an initial condition, and then I do this iteration. And in each step, I do some work, there is some heat flow, there is some entropy production. If I add them, and I know that I will converge to an equilibrium state, so I can add them, and they converge. So this is the total work that I do in the process that start with the system in the state rho s and converge to this equilibrium, right? So it is there, it converges. When I continue to do more steps, I'm not doing more work, that's why it stays bounded. And the same with the entropy production and the heat, right? So I show you that it is possible to have systems that do not relax to thermodynamic equilibrium, but they are driven to thermodynamic equilibrium, right? An agent has to do some work to drive the system to the equilibrium state, but once the system is in the equilibrium state, the agent is performing his map, but he's not doing work to do this map, to perform this map, right? Okay, and this already I said. So what I have to do now is, okay, I convince you that it is possible to have an equilibrium state, to reach an equilibrium state by doing work, but now I have to convince you that this state can be active, right? So to check if it is active, I have all this machinery to compute the ergotropy of the state. And I will do also, I will not go into details, but I define also an efficiency of the process. So if I have the active state and I do the optimal cyclic unitary process to extract the ergotropy, we know that the system will be left in a passive state, right? So what I want to consider is a process of recharging the battery from the passive state again to the active state. It's like if I want to recycle my battery to use it many times, I will have to always charge it from this uncharged state. So I consider this process, the recharging process, and I define an efficiency by the ratio of the ergotropy of the equilibrium state to the work that I have to do to reach this ergotropic equilibrium state. And one can show that this efficiency is always between 0 and 1. So now I will show you an example where, in fact, the equilibrium state that I reach is active. And I think it's a very interesting equilibrium state. So to simplify the unitaries that the agent do between the system and bath, I consider that the time dependence of this potential is flat, so it's a constant in time. And then I can satisfy the condition to have an equilibrium if I satisfy these two conditions here, right? I have to find an operator that commutes with the Hamiltonian, and that when it is added to the Hamiltonian of the bath, it commutes with the coupling operator between the coupling energy between the system and the bath. So I take here as my battery a two-level system. The bath is also a collection of two-level systems, all of them in the Gibbs state. And I compute the work I do in each step, the heat flow, the entropy production. These are per step, so they goes to 0, right? So when I'm reaching equilibrium, I'm not doing work, entropy is not being produced, etc. And what is the equilibrium state? Well, this V has this property. It is, and you see that because the system and bath are kind of the same are symmetric, and the coupling is symmetric, so it is the same if I commute it with HS here or HB. But these relations means that H0 is minus HS. So I think it's very interesting. The system is, while is arriving to a thermodynamic equilibrium, which is this state, a state with an effective positive temperature. And so here I plot the population's dynamics. So the ground, in fact, the initial condition of this battery was also the Gibbs state, and it started with the ground state with the population 0.8 and the excited state at population 0.2. And as the dynamics goes on, the population is inverted, right? So I show you that it is possible to have active equilibrium states, and this, to reach equilibrium states by doing work, driving the system to an equilibrium state, and reaching active equilibrium states. So I will not compute the ergotropy of this state, but you realize that it is an active equilibrium state. So with this, I'm at the end of my talk. So just to comment on conclusions. So it is possible to engineer processes that are driven to states of thermodynamic equilibrium, and these states, they may be active, right? I show an example where the active state that you reach is this state with an effective negative temperature. I give the example for just 2 qubits, but in fact, you can generalize it. What you need to ask is to find is a coupling potential energy where the system and bath operators satisfy these conditions. And because they have to have the same spectrum of Bohr frequencies, the obvious things will be to consider that this bath is a copy of the system of interest. I commented that one can define an efficiency, and for the process I discussed here, the efficiency is 1/2. And I didn't have time to discuss this, but one can show that this efficiency, which is the ratio between the quantity that one is interested in, the ergotropy, and the work one has to do to get this quantity, so that the efficiency of the process goes to 1 only when the ergotropy goes to 0, which is kind of the usual thing that's happening in thermodynamics. The efficiency of a Carnot engine is 0, but then the power is 1, but no, it's Carnot, sorry, but then the powers go to 0, etc. It's the same kind of situation. And that's it. Thank you.
Thanks for the nice talk. I'm just curious with your example.